going to start looking at the wonderful area of calculus. We're beginning off with this thing called the gradient function. And basically, this is it. We know that the function, y equals function x, well, basically that's measuring the distance of the graph from the x-axis. So it's telling us what the y value is. With a gradient function, and there's one of the ways we denote it with a dash there, so f dash x, measures how steep the graph is at that particular point. In other words, the gradient. So it's the rate that that distance is changing, more commonly known as the derivative. But that is what the gradient function is. Now, to start off with, we're going to use geometry to find it. And we can do that quite easily with lines and semicircles. We use that as a starting point because if it's a line, well, I know a horizontal line is simply the function is a constant number. I also know the slope of a horizontal line is 0. So I don't really have to do anything. I know that the gradient function will always be 0. If it's an oblique line, well, we know all oblique lines can be written in the form y equals mx plus b, and the slope of the line is m. So therefore the gradient function would be m, whatever the slope is. So lines are very easy. Semicircles. So here's our standard one centered at the origin with a radius of r, and we know its equation, square root of r squared minus x squared. Now it's a bit different to a line because depending on where we are, the steepness of that graph changes. When we talk about the steepness or the slope of a curve rather than a line, what we're really talking about is the slope of the tangent at that particular point. So whatever that particular line is, its slope would be the slope of the curve. Well, because it's a semicircle and we know some things about circles, then I can work out the slope of that line because I do know that the radius is always perpendicular to the tangent at that point of contact. And I can work out the slope of the radius. It's rise over run. Whatever the y value is, function x over the run, the x value. Therefore the slope of the tangent would be the negative inverse of that. Negative x over function x. And we know what function x is. So we can take it even further. Our function is square root of r squared minus x squared. Therefore the gradient function will be minus x over the square root of r squared minus x squared. So that's semicircles. But unfortunately we've got all these other graphs we want to investigate, and at this stage, before we've done anything else, all we can do is really estimate it using secants. Let's look at a quadratic, which of course is a parabola. There's a point 2,4. Now what I'll do is I'll pick a couple of points either side and create a secant. So let's say I picked 1, 1 and 3, 9. Now if I was to join those up, I would end up with an estimate for the tangent. Now, it might not be right, but it's going to be close. Now the slope of AB, because of the way I picked it there, will be 4. And actually that is correct. But of course the accuracy of my answer will totally depend on my choice of the 2 points. If I could have picked another 2 points and got a terrible estimate. It just turned out that this one, yeah, it was right. And that's all to do with symmetry. So if I've got x squared, there's any point on the parabola. If I pick a point the same distance either side, so one's going to be x plus h and one's x minus h, then I could generate a formula and it turns out to be 2x, and that is the gradient function for the parabola y equals x squared. And again, it worked because of the symmetry of choosing those points, and that's fine for a quadratic. What about a hyperbola? There's a point 2.5. If I go symmetric either side, I mean visually I think we can see that that doesn't look like the same as the tangent would be. Let's see, minus 1/3 is what I get for AB. Actually, is that a good estimate? No, it's not. It actually turns out it's negative 1/4 at that point. That symmetry idea is not working with my hyperbola. And in fact, with the hyperbola, we've got another issue, because this curve is not continuous. And so when it's continuous, one thing we want to do is have the 2 points at least on the same branch. Because imagine I did this. If I chose C on the other one, I mean, have a look at that for an estimate. Terrible. Not even the same sign. One's negative and one's positive. So not a great estimate. So if you have an accurate graph, then possibly it's best just to draw the tangent in and work out rise over run. Read off the graph. But that relies on being a really accurate graph. So that's our starting point. So 9A will do that.